All right, so welcome back to the second half of Neil Fan's talk. Please take it away, Neil.
Okay, let's continue. So we turn to our main computational structure, Bumpless pipe dream fragments. In the work of Wyser and Yong in 2014, many fundamental frameworks were built, such as polynomial representatives, upsilon gamma xy, and the non-equivariant Schubert expansion of upsilon gamma, and the commutative algebra interpretations of upsilon gamma. However, there remain some questions, such as computational models for upsilon gamma xy and equivariant Schubert expansion of upsilon gamma. We will answer question 2 by using Bumpless pipe dreams. A Bumpless pipe dream for our permutation W in the symmetric group is a tiling of the n cross n grid by the following 6 tiles. Bumpless pipe dreams were introduced by Lan Li Somozono in 2018, and they can use to compute double Schubert and quadratic polynomials. See also Weekend. Here is an example of all the Bumpless pipe dreams for the permutation 1, 3, 4, 2. There are 3 Bumpless pipe dreams, and the Schubert polynomial is the weighted sum of the Bumpless pipe dreams. The weight of a Bumpless pipe dream is we weight the empty tile. For empty tile at ij, the weight of the tile is xi minus yj. For example, this empty tile is x3 minus y2. And for example, this empty tile, the weight of this empty tile is x2 minus y1. So the Schubert polynomial of 1, 3, 4, 2 is the sum of these 3 weights. Bumpless pipe dream fragments are just exactly Bumpless pipe dreams supported on a partition. So this is a rectangle. This Bumpless are square, and we consider Bumpless pipe dreams on a partition. This was first considered by Weekend in this paper. So our novel observation is that Bumpless pipe dream fragments are naturally indexed by clams, not by permutations. So to read off a clam from a Bumpless pipe dream fragment, we just pull straight the southeast boundary of the partition, pull straight, and replace each step by a node. This is a node, this is a node. And if there is a pipe connecting 2 steps, we draw an arc between the 2 nodes. For instance, there is a pipe connecting this step with this step. So we draw an arc connecting them. So it's easy to see that from each Bumpless pipe dream fragment, we can obtain a clam. Conversely, for each clam, there is a unique Young diagram obtained by replacing each left endpoint and plus signs with vertical steps, and replace each minus signs and after connecting the arcs, we replace the horizontal steps by minus signs. We replace the unmatched plus vertical steps by plus signs. This is a vertical step. It is unmatched. So we replace it by a plus sign. So from a Bumpless pipe dream fragment, we obtain a clan. Each clan corresponds to a Young diagram just by replacing left endpoints with horizontal vertical steps, and minus signs with horizontal steps, plus signs with replaced with horizontal vertical steps. So we use BPT gamma to denote the set of Bumpless pipe dream fragments of gamma, and the lambda gamma be the Young diagram indexed by gamma in the P cross Q rectangle. This is a Bumpless dream fragment. Like Schubert polynomials, we define Klein polynomials as the weighted sum of all the Bumpless pipe dream fragments. But for convenience, for an empty tile in the Bumpless dream fragment, the weight of this empty tile is xi minus x n minus j plus I. Is in the Schubert case, the weight of the empty tile is xi minus yj, but the weight of this in Klein polynomial is xi minus xn minus j plus I. For instance, for this Klein, there are 3 BPT fragments, and the weight of this is the empty tile. This empty tile, the weight of n is x1 minus x9, not y1, xi minus y x9, and this is x3 minus y7, and for this empty tile, the weight is x1 minus x8, etc. So the Klein polynomial is the sum of these 3 polynomials. It's easy to say that under change of variables, Klein polynomials include double Schubert polynomials of partial permutations, a special case. When the shape of the BPT fragment is a rectangle, we can obtain a partial permutation. And Klein polynomials, after change of variables, change this factor into y, where we can obtain the double Schubert polynomials. Our first main result is a combinatorial formula for the localization of upsilon gamma at the minimum W, such that upsilon gamma localized at W is not equal to 0. Localization is obtained by replacing x1 with y sub w1 and x2 with y sub w of 2. So this is the localization. So this is our first main result. The localization of upsilon gamma at V gamma is the product of the Klein polynomial of gamma with this factor. This factor is lambda gamma is a partition correspond to gamma, and the bar means that the complement of lambda gamma in the P cross Q rectangle. Let us see an example. This is the Klein, and this is the V gamma. We label the left endpoints and plus times first. 1, 2, 3, 4. And there are 3 BPT fragments. And the weight of this empty tile is y1 minus y9. And this is y3 minus y7. So these 3 factors correspond to the Klein polynomial. And this factor is the boxes outside the partition in the rectangle. For example, for this box outside the partition, it corresponds to y5 minus y2. And for this empty box outside the rectangle, the weight of this tile is y6 minus y3, so etc. So this is the localization. It's natural to ask what's the relation between our localization formula with the famous Bumpless localization formula. When gamma is non-crossing, Y gamma, the orbital closure Y gamma is a resident variety. In this case, the Klein polynomial is just the product of 2 Schubert polynomials, and after localization, we obtain this product. And this agrees with Bumpless formula. Since in this case, the crossing tile does not appear, this gamma is not crossing, and we can make a bijection between BPT fragments with this pipe dream fragment. after this replacing, you can see that this factor, this localization corresponds to the boxes outside of the rectangle. And this term coincides with Billy's formula. We can read off a reduced word of U gamma from this just the crossings. So we consider the Schubert expansion. The classes of B orbit closures, that is the Schubert classes, form a basis of the equivariant cohomology. A natural question is to find a positive expansion of an effective class. For the non-equivariant expansion, the coefficient of Y gamma is obtained by Brion. We give the equivariant Schubert expansion of Y gamma sub T. That is the double Schubert polynomial expansion of upsilon gamma. By Brion, in the non-equivariant setting, all the Schubert coefficients are 0, 1, which is an example of multi-city-free subvarieties. Look like this. The coefficients are always 0, 1. So in general, it's not clear what's the equivalent analog of multi-city-free subvarieties. We give a complete answer of the question 2 of Wyser and Yong. So in the equivariant Schubert expansion, the coefficient C sub gamma Wy is either a Klein polynomial or 0. So what's a Klein polynomial? It's indexed by gamma prime. Gamma prime is if gamma prime equals Wx on gamma, and V gamma prime is identity, and the length of gamma prime minus the length of gamma equals the length of W. Let's say an example. So, for example, if the Klein equals this Klein, we want to expand its upsilon gamma, yes, into double Schubert polynomials. So we just consider all the Kleins above this Klein in the weak order. That is the upper order ideal of this Klein. And we choose the Kleins gamma prime such that V gamma prime is the identity. There are four Kleins whose gamma prime is V gamma prime is identity, because we label the first nodes and plus and first nodes. So this gamma prime, this V gamma prime is identity. So just for example, we choose this one. This gamma prime has two BPD fragments, and its Klein polynomial is this tile is Y1 minus Y5, and this tile, the weight of this tile is Y2 minus Y4. So the coefficient of this W, S4, S3, S2 is the Klein polynomial of this Klein. This is the equivalent Schubert expansion. The coefficient as the Klein polynomial corresponding to the permutation. So the sketch of the proof, the proof is by induction. The initial case is by studying the local structure of the closed K orbits at the identity. And the inductive step is by studying the local change of a Klein. We construct a transversal slice which intersects every orbit transversally. And we show that the intersection, the dashed lines are isomorphic to a matrix supervariety. And so we obtain a double Schubert polynomials. After localization, we got our Klein polynomial. So this is more detail. This is the K, which is a Bragg diagonal matrix. 0p, 0q. And the P minus is this diagonal matrix. No, this is the lower triangular matrix. And NP minus is the nilpotent radical of P minus. It's easy to say that G over B includes P minus B over B, includes NP minus B over B, and includes a point. So we decompose the localization at the identity into the following three maps: F star, G star, and H star, where F, G, H are inclusions. To study F star, it's easy to say that P minus B over B is an open neighborhood of the point in G over B. So the restriction is just intersection. And since we consider V gamma is identity, so we consider V gamma is identity. So this intersection is always non-zero. So this is F star. For G star, as mentioned, we show that the NP minus orbit is closed in P minus B over B, and it intersects all orbits transversely. So the restriction is intersection. So the effect of G star is Y gamma intersect NP minus B over B, since this is transversally. Finally, for the H star, NP minus is isomorphic to the set of Q cross P matrices, and we show that the intersection Y gamma intersect with NP minus B over B correspond to the matrix variety. So the polynomial representative of this orbit is a double Schubert polynomial. So after localization, we obtain our Klein polynomial. This is the sketch. So some applications. We can obtain, when gamma is non-crossing, Y gamma is recurrent variety. So we can obtain Schubert structure constant is essentially a Klein polynomial. When gamma is non-crossing, the Schubert polynomial of U gamma times any permutation V, the Schubert polynomial of any permutation V. In this expansion, the coefficient of W naught V gamma is a Klein polynomial. So it's worth mentioning that Penchnik and Wiegand introduced backstable clamps, and they use backstable clamps to give a Littlewood resistance rule for the product of two Schubert polynomials indexed by inverse Grassmannians. They consider the single case. It's we want to extend the result to the equivariant case, but this is we just obtain one coefficient is a Klein polynomial. We don't know the other coefficients now. So this is our first result application. The second application is the smooth criterion. We show that for Klein gamma, the following statements are equivalent. First, the orbit closure Y gamma is smooth at V gamma. And the second is the gamma has exactly one Bumpless pipe fragment. That is, there is no space for the droop operation. Since all the Bumpless pipe can be obtained from the Rose pipe by applying droops, so we can also obtain all the BPD fragments by applying droop operations from the Rose BPD fragment. So if there is no droop possible, then gamma has exactly one BPT fragment. That is Rose BPT fragment. And the third, the clan gamma avoids the following 5 patterns. So this is our corollary. The proof. Our corollary can recover the classic smoothness criterion of Backgaven and Wu and Wyser. They show that if gamma is non-crossing, the orbit closure Y gamma is smooth. That means smooth at every point. If and only if gamma avoids the following 5 patterns. That essentially, if gamma avoids the 5 following patterns, gamma is a union of rainbows. Just a sequence of listing cover some signs with the same sign. This is a listing. So if gamma avoids these patterns, then gamma is essentially a union of rainbows. So they show that when gamma is a union of rainbows, Y gamma, the orbit closure Y gamma is smooth. So we can obtain the result as follows. By Wyser and Yong, by Wu and Wyser in lemma 3.1, they also Knudsen, Wu, and Yong. Our recent variety is smooth if and only if it is smooth at the maximum and the minimum permutations. Just we check 2 permutations. So our recent variety is avoid the crossing, and if it wants to be smooth at V gamma, it must avoid these 5 patterns. This is our first corollary. And by duality, we can obtain that if it wants to be smooth at W naught U gamma, we just switch the plus signs and minus signs. So it avoids these 5 patterns. So combining all these together, we obtain these 4 patterns. So thank you. That's all.
Thank you very much. Thank you very much for a beautiful talk. So